Okay, I think we're ready to go now. So let's give it a few more seconds for people to arrive. Okay, I think we can get started. Okay, welcome everyone to our next Safari Live seminar. We're restarting in the fall, although it's not exactly fall yet, but it's almost fall, with Ataberk Olgun's seminar on QUAC-TRNG, high-throughput to random number generation and using quadruple row activation in real DRAM chips. Ataberk has led this work, which was published at ISCA this year in 2021. And he did this work while he was an intern, and after he was an intern with Safari. He's been with us for a few years now, right, Ataberk?
Yes, that's true.
Yeah, and more recently, remotely, of course, and he's going to continue working with us on exciting topics. I think we can get started. Anything else you want to share?
No, I think thanks for the introduction, Onur, and you already gave the title of our work, so I will just start with an executive summary, I think.
Sounds good. Go ahead.
Yep. So the problem here, we're motivated by the low-cost nature of DRAM-based random number generation. They can provide low-cost random number generation to a variety of systems. However, when we look at prior work, we see that they cannot provide low latency and high throughput to random number generation, as these ranges are either sampling fundamentally slow physical processes, or they cannot effectively harness entropy from DRAM rows. And our goal in this work is to develop a high throughput and a low latency TRNG that can be implemented using commodity DRAM devices. And we make the key observation that a carefully engineered sequence of standard DRAM commands can activate 4 consecutive DRAM rows in quick succession. And we call this new phenomena QUadruple ACtivation, and we refer to it as QUAC for short. And our key idea in this work is to use these QUAC operations to simultaneously activate DRAM rows that contain conflicting data to generate random values on DRAM sense amplifiers. So we developed QUAC-TRNG, which repeatedly performs these QUAC operations and post-processes the results using a cryptographic hash function to generate 2 random numbers at high throughput and with low latency. We evaluate QUAC-TRNG's throughput and quality using 136 real DDR4 chips from 17 DDR4 modules. And our results show that QUAC-TRNG can achieve up to 5.4 gigabits throughput per DRAM channel, outperforming the state-of-the-art by 15 times for their base and 1.4 times for their throughput-optimized configurations. QUAC-TRNG also generates 2 random numbers with very low latency, and we use the standard randomness tests developed by the National Institute of Standards and Technology to measure the quality of QUAC-TRNG. Here's an outline of this talk. To start with, I will briefly introduce 2 random number generation, and then discuss why we need DRAM-based 2 random number generation in current computing systems. By the way, I'll stop to take questions in the outline slide, but the audience also can feel free to interrupt me to ask questions at any time. There are many ways to define randomness, and therefore what makes a random number random. And for simplicity, we will go with this definition here: a sequence of bits without any discernible pattern. As an example, you can probably notice that the first 2 bit streams presented here look less random because the bits that make up the numbers follow a pattern. However, the 3rd bit stream does not seem to follow a pattern, and therefore we could say that it's random. To produce these random numbers, we use what's called a random number generator. A random number generator outputs random numbers, and this can be a device or a program running on a computer. To see how random number generators generate random numbers, we will briefly look at 2 categories of random number generators. Pseudo-random number generators continuously perform arithmetic operations on an initial seed value to maintain a state, and then output a random number based on the state. 2 random number generators simply sample random physical processes to generate random numbers. Since PRNG output depends on this initial seed, someone with malicious intent could fully regenerate the stream of random numbers. While this is not the case for a TRNG, as it's not possible to regenerate the output of this true random number generator by observing the physical process. By doing so, by observing the physical process, we expect to only generate another random number. And from a cryptographic perspective, this makes TRNGs more secure. One important characteristic of a true random number generator is its quality. And we need a way to measure the quality of a TRNG to systematically distinguish between good and bad TRNGs, or low quality or high quality and low quality TRNGs. A common way to do that is to conduct statistical testing on TRNG outputs. And these tests analyze the random bit streams and evaluate a number of their statistical properties to find patterns. Typically, the test will either fail or pass, depending on how well some statistical properties are satisfied by the random number sequence. To summarize, the idea behind TRNG quality assessment is to make sure, as much as possible, the output bit streams don't contain any patterns that can be identified by computers. And we call TRNGs that produce such bit streams high quality. High quality through random number generation is critical to many applications. And some examples are cryptography to generate cryptographic keys and signatures. In scientific simulations, provide Monte Carlo methods with random numbers that well fit a desired distribution, and machine learning to perform randomized training on neural networks and in genetic algorithms. Now, true random numbers can only be obtained by sampling random physical processes. And unfortunately, not all computing systems are equipped with this dedicated TRNG hardware, such as low power embedded systems and commercial processing and memory systems. And this greatly limits the application space supported by these systems, and it also weakens the security guarantees provided by these systems. Now, DRAM is widely used as main memory in a wide range of computing systems, and TRNGs based on DRAM enable true random number generation within DRAM chips. This is particularly useful for supporting true random number generation in constrained systems, as they can be implemented with low hardware cost. DRAM-based TRNGs also provide true random numbers at high throughput, which can open the application space in computing systems that lack dedicated TRNG hardware. Finally, DRAM-based TRNGs are synergistic with processing in memory systems, which typically perform computation directly within a memory chip and improve the overall system performance by avoiding unnecessary data movement. True random number generation within DRAM devices enable PIM workloads to sample true random numbers directly within the memory chip. And by doing so, they avoid inefficient communication to other possible off-chip TRNG sources, like the one you would find in your processor. And thereby it enhances the overall security and privacy of PIM systems. Now I'll go over the relevant background on DRAM organization and TRNGs in the next few slides. And this will also include relevant information on prior DRAM TRNGs. If there are no questions, I will continue. Okay, so typically a processor's memory controller communicates with a set of DRAM chips within a DRAM module through a memory channel. Each DRAM chip contains multiple banks that share a common chip I/O interface. DRAM banks are organized into subarrays that consist of a set of word line drivers and sense amplifiers. Subarrays are partitioned into DRAM mats, which are collections of DRAM cells that are separated from each other by word line drivers. DRAM cells are laid out onto a two-dimensional array of word lines and bit lines within a DRAM mat, and a row of DRAM cells is referred to as a DRAM row. And here's a simplified diagram of a DRAM cell. Now we will look at how we access this DRAM cell. And this is a diagram that shows how a DRAM cell is connected to a sense amplifier, which is used to read out data from the capacitor. A DRAM cell contains two components. The capacitor stores data, and the access transistor determines if the cell is being accessed. The access transistor is controlled by the word line, which is enabled to connect the DRAM cell to its bit line. And the bitline bar is essentially the inverse of the bitline, and it's used in the sense amplification process. The DRAM sense amplifier has an enable signal which determines if the sense amplifier is currently active. Initially, both the access transistor and the sense amplifier are disabled, and both ends of the sense amplifier are maintained at half VDD. In this example, the capacitor is fully charged, and to access the cell, we first enable the word line, and this connects the capacitor to its bit line. Since the capacitor has a voltage level higher than the bit line, the charge starts flowing from the capacitor to the bit line, resulting in the bit line voltage to deviate slightly towards VDD. When we enable the sense amplifier, it will compare the voltage levels of bit line and bit line bar and amplify the deviation until bit line voltage reaches VDD. Since the capacitor is still connected to the bit line, the amplification process also restores charge in the capacitor. We will now look at how DRAM operates at the scope of a single subarray. Because memory controllers typically access DRAM cells in the granularity of a cache line or a cache block, we combine consecutive DRAM cells to form cache lines in this diagram. On the bottom, we have a timeline of DRAM commands. First, we activate the first row to copy its cache lines to the sense amplifiers. At this point, we can read data in cache line granularity from the sense amplifiers by sending read commands. To access another row, we must first precharge the DRAM bank, which closes the open DRAM row and sets the bitline voltage to half VDD. We can now activate the second row before reading data from it. Now, to ensure correct operation, we must obey certain timing parameters that define intervals between DRAM command pairs. Two important timing parameters are TRAS and TRP. And TRAS is the time required for the charge to become restored in the capacitors on the open row. And TRAS dictates the amount of time we need to wait between successive activate and pre-charge commands. TRP is the time it takes for a bitline to become pre-charged to half VDD, such that a new activate command can be issued to open a DRAM row. And successive pre-charge and activate commands on the command bus must be separated by at least a TRP amount of time. So true random number generators sample physical processes as we described earlier. These processes behave randomly, meaning that we cannot identify any patterns inherent to these processes. So some examples are thermal noise in electronics, Brownian motion where particles move uncontrollably in fluids as they constantly collide with each other, and even an array of lava lamps where the movement of wax inside the lava lamp is random. Now, there's usually bias in the output of the true random number generator due to bias in the randomness source and the sampling device. Here, bias means that the digitized output would favor either one of the binary digits, ones or zeros, more than the other, as you can see in the red box. Now, this in turn results in low quality random numbers. And to remove bias in TRNG output and to improve TRNG quality, we typically use post-processing mechanisms. There are two example post-processing methods. One is the cryptographic hash functions. They, in general, operate on multiple blocks of data using arithmetic shuffling and mixing operations to produce a shorter hashed output. Since these functions are designed to map the input bits to an output bit as uniquely as possible, they can be used to remove bias in TRNG outputs. Another post-processor is the von Neumann corrector, which partitions the input bit streams into 2-bit pieces and applies the encoding in this figure to remove redundant bits and to finally improve the quality of the random number generator. We will look at what entropy sources can be used within DRAM devices to generate true random numbers, or what has been used so far. So a set of DRAM TRNGs use retention failures as their entropy source. Capacitors in DRAM cells leak charge to the nearby circuitry over time and need to be refreshed. The key idea of retention failure-based TRNGs is to accumulate these failures over time and generate random numbers as a digest of the positions of the failing cells. Since charge leakage is fundamentally a slow process, these TRNGs are limited in the throughput they can provide. Another entropy source is the values that are observed in DRAM arrays immediately after the device is powered on. TRNGs based on this are also slow because it takes time in the order of microseconds to power cycle DRAM devices. Failures due to violated timings in DRAM can also be used as entropy sources, and these sources are primarily useful because they're fast, since we can induce timing failures as frequently as the DRAM command latencies allows us to, which is in the order of nanoseconds. We will look at this third category of TRNGs to understand the key limitations of the state-of-the-art. So far, two DRAM TRNGs that use timing failures as their sources, entropy source exists. DRANGE uses activation latency failures, and Bahar-Talukder's work uses pre-charge latency failures. I'll describe how DRANGE works, and to start with, we will understand how access latency or TRCD failures happen. Here is another DRAM cell, the same DRAM cell, which shares its charge with the bitline when we activate it. Initially, the bitline voltage is kept at half VDD. When the word line is driven high or activated, the capacitor begins to share its charge with the bitline. The sense amplifier is then enabled, and the voltage differential on the bitline is amplified to an IO-readable value. In order to ensure correctness of operation, the memory controller can only read data TRCD time after this activation. We could read this data earlier when it reaches a readable voltage threshold, depicted as Vmin, but we want to make sure that there's enough guard band such that other cells that may be weaker due to process variation will not fail when accessed TRCD time after activation. If we are to read with a TRCD reduced below manufacturer recommended values, we begin to induce latency failures in the weaker cells. And cells that are read when their bitline's voltage is lower than Vmin have a probability of failure. And this probability increases as we further reduce the voltage level, further reduce TRCD below the voltage threshold. When we look at the DRAM array, we see that cells with varying failure probabilities are distributed all over it. And some of these cells fail with a 50% probability when accessed with reduced TRCD. And the key idea of DRANGE is to use those cells that fail truly randomly to generate random numbers. Talukder's mechanism uses the pre-charge or TRP latency failures to generate random numbers. The key idea here is similar to DRANGE. Basically, we identify cells that fail with close to 50% probability when we access them with reduced TRP. Now, the others don't discuss in detail where exactly the randomness comes from, but I will quickly describe one hypothesis. So here's a diagram that shows the bitline voltage across many stages of DRAM cell access. The authors, by accessing a row with a reduced TRP, caused the newly activated DRAM cells to share their charge with a not yet pre-charged bitline, meaning that the bitline voltage is not VDD over 2 yet. Now, due to this, some of the sense amplifiers end up amplifying a bitline voltage below their reliable sensing thresholds, which results in random numbers. And this will become more clear as I describe how we use QUAC to generate random numbers in the upcoming slides. These TRNGs have key limitations that prevent them from providing the highest possible throughput. DRANGE poorly utilizes the DRAM activation granularity, which is typically 8 kilobytes in a system. Since with a reduced TRCD, DRAM read commands can only generate random values in a 64-byte cache block size region, the remaining cells of the row cannot be used to generate random values. So the throughput of DRANGE is essentially limited by DRAM access latency, as we need to frequently activate and pre-charge DRAM rows to generate random numbers. Talukder's TRNG can generate random values across the whole DRAM row using pre-charge latency failures. However, it cannot induce metastability on many sense amplifiers, and the DRAM row ends up with scarcely distributed small amounts of randomness. And therefore, the throughput limiting factor in Talukder's TRNG is the poor quality of the randomness source. So we posit from this analysis that a high throughput DRAM TRNG should well utilize the DRAM activation granularity and induce metastability on many sense amplifiers. Next, I will describe the key mechanism of our high throughput TRNG that enables us to beat both of the previous requirements. Okay. So we observe that a valid sequence of DRAM commands can activate 4 consecutive rows in quick succession in real DRAM chips. And we call this new phenomenon QUadruple activation, and we refer to it as QUAC for short. To perform a QUAC operation in DRAM, we first send an activate command, then we send a pre-charge command that greatly violates the TRAS timing parameter. Now, instead of waiting for the default 35 nanoseconds, we wait for less than 3 nanoseconds. We follow this up with another activate command, this time violating the TRP timing parameter. In doing so, we're able to open 4 DRAM rows with just 2 activate commands. We identify 2 characteristics of QUAC operations. First, QUAC can only activate the set of 4 rows whose addresses differ only in their 2 least significant bits. So here's an example to simplify this. The diagram shows the organization of a set of rows in a subarray at a high level, and QUAC can only activate a set of rows with the same color here, such as rows 0, 1, 2, 3, and rows 4, 5, 6, 7. However, QUAC cannot activate any set of rows that are differently colored, such as rows 2, 3, 4, and 5. The second characteristic is that QUAC must activate the 2 rows with addresses that have their 2 least significant bits inverted. Here we use the same color to highlight the least significant 2 bits in row addresses that can be targeted by activate commands to perform QUAC operations. When the first activate targets row 0 and the second activate targets row 3, we observe valid QUAC operations because the least significant 2 bits of these 2 addresses are inverted. Similarly, when the first activate targets row 2 and the second activate targets row 1, we observe valid QUAC operations. When we're using these 2 address combinations, the order of the activate commands do not matter, meaning that we could activate row 1 first and row 2 second. However, these are the only combinations of addresses that can be used to perform QUAC operations. We conduct experiments using our DRAM testing infrastructure, which I will talk more about in the upcoming slides, and observe valid QUAC behavior on 136 DDR4 chips from 17 DRAM modules. Now to explain how QUAC might be supported in current real DRAM devices, we develop a hypothesis. And this is based on the use of hierarchical wordline schemes that enable high density and high performance DRAM operation. In this hierarchical wordline scheme, a master wordline potentially derives multiple local wordlines. We will look at an expanded view of a DRAM mat along with the wordline drivers it's attached to understand this better. The master wordline drivers attached to either sides of the DRAM mat drive the master wordlines, whereas the local wordline drivers drive the local wordlines that enable the access transistors in DRAM cells. These local wordline drivers are enabled with a combination of the master wordline and a certain control signal, which we denoted as S0, S1, S2, and S3 in this diagram. Now we will look at how the DRAM row decoder might be setting these control signals to enable QUAC in real DRAM chips. So our hypothetical decoder operates on the least significant 2 bits of the row address signal to set the control signals that drive the local word lines. The decoder logically operates in 2 steps. First, it pre-decodes the least significant 2 bits to form intermediate signals. Second, it combines the intermediate signals to drive the control signals. The pre-decoder outputs the least significant 2 row address bits along with their inverses and latches these signals. And the row decoder combines the intermediate signals using 2 input AND gates. We will now see how an activate, precharge, activate command sequence that we use to perform QUAC operations can enable all 4 control signals S0 through S3. So we first issue an activate command to row 0, which sets the latches that drive A0 bar and A1 bar. This in turn enables the S0 signal, which is set by the bitwise AND gate that operates on A0 bar and A1 bar. The AND gates that drive S1 and S2 have partially set inputs. However, since A0 and A1 are not yet enabled, these signals, these gates do not drive their corresponding control signals. So with the first activate command executed, this decoder drives a single local word line. Following the first activate, we send a precharge command while greatly violating the TRS timing parameter. The precharge command cannot disable these 2 latches as there's not enough time due to violated TRS. We then quickly send another activate command, this time greatly violating the TRP timing parameter. This interrupts the precharge process, and the latches that drive A0 bar and A1 bar remain enabled. Then the least significant 2 bits of the addresses are set to 1, which enables the latches that drive A0 and A1. Since all intermediate signals are driven, all bitwise AND combinations of these signals are also enabled. With the execution of the second activate command, the remaining 3 word lines, S1, S2, and S3 are enabled, resulting in quadruple activation. Now I will describe how we develop QUAC-TRNG based on QUAC operations.
Okay, Ataberk, I think we have a couple of questions in the YouTube chat, so I'd like to quickly go through them. So the first question we have here is that, do these failures, including for the prior approaches that you talked about before, and also with QUAC-TRNG, do they happen frequently enough to ensure a good supply of random numbers?
Yes, so speaking of the prior work, for example, DRANGE, they evaluate this using real DRAM chips also, and see that with a single DRANGE loop, let's say, activate and read with reduced TRCD, can induce up to 4 truly random values in a single cache block. So I guess you could say that it's frequent enough because an activate and read command takes in the order of nanoseconds. And it's also similar for the Tolokter's mechanism, as well as it's for QUAC-TRNG. I don't know if that answers that question. Because we're inducing these failures in the order of nanoseconds, and because there are, let's say, random value generating bit lines, you could say that these random values are generated frequently, yes.
Yeah, thanks. I think that makes sense. So if there's any follow-up questions, please, go ahead and post that in the chat. So a second question that we have is talking a little bit about the underlying physical mechanism for this QUAC phenomenon that you've observed. So the question is in 2 parts. So the first part observes that in a recent paper published about understanding rowhammer, this paper is called On DRAM Rowhammer and the Physics of Insecurity. This paper points to 2 potential physical phenomena that are responsible for the rowhammer error mechanism. And in this case, they talk about electron diffusion and capacitive coupling. And that's in the case of rowhammer, right? So does this random number generator rely on similar underlying phenomena?
So the explanation we have, which I will describe in the next few slides, I think refer to a different phenomena. However, don't think we can leave out anything that's random within DRAM chips. And we cannot, I think we can't dismiss them, that they're not contributing to the randomness we observe in both prior TRNGs, DRAM-based TRNGs, and QUAC-TRNG. I am not like an expert on the underlying phenomena for the rowhammer vulnerability, but that's, I think, my opinion on this. So we probably cannot really dismiss anything that's random that's going on in the DRAM chip, especially in the DRAM array.
Right. I think that makes sense. So as a follow-up to this, so I think the person asking the question sort of rephrased it a little bit. So we're asking about the source of the randomness here, right? So how can we sort of guarantee that this is a truly random process? So does this randomness, for example, come from having a lack of information about the internal state of DRAM, or from a physical process, such as, for example, provided Fowler-Nordheim tunneling, or some unknown physical process?
Yes, so I'm not aware what that process refers to exactly, but in the end, I think, as I mentioned in the previous slides, we have these statistical tests that we conduct to understand if a generator is indeed producing random numbers. That's something we use to measure quality, and indirectly the let's say the source of randomness being something really physically random. We are sampling random physical processes here, both the prior DRAM-based TRNGs. For example, the retention failure-based mechanism, I think there's this variable junction leakage phenomena that exists in CMOS or like anything transistor-based, which is truly random. And if we can't dismiss anything that's random that's within DRAM chips as something that's not contributing to the randomness we observe here, I would say that we are sampling a truly random process with these DRAM-based TRNGs. Yeah, that's how I would like to answer, I think.
Okay, no problem. Sorry.
Just to add, so I will describe the explanation we have in the next few slides, and we can perhaps go back to this discussion afterwards.
No problem. I think, yeah, so that's all we have for the questions right now. So please go ahead and continue.
Okay. Yep, so moving on with QUAC-TRNG. So first, I will describe over an example how we generate random values in DRAM sense amplifiers using QUadruple activation. This diagram depicts a set of DRAM cells on the same bit line on 4 simultaneously activated DRAM rows. Initially, the even address rows are initialized with logic 1, and the odd address rows are initialized with logic 0. Now, the bit line and the bitline bar is set to half VDD, and the figure on the right depicts the difference in voltage between the 2 sense amplifier terminals over time. The gray dashed lines depict the reliable sensing thresholds that the bitline voltage needs to exceed for the sense amplifier to correctly sense the values on the bitline. Since bitline and bitline bar are set to half VDD, the voltage difference here is initially 0. We start by sending an activate command to row 0, which enables the word line, and consequently the DRAM cell on row 0 shares its charge with the bitline, raising the bitline voltage slightly above half VDD. Next, we send a pre-charge command, quickly followed by another activate command, this time to row 3. The second activate command enables the remaining 3 rows and keeps the first row open as it interrupts the pre-charge process. Now, the sense amplifier is enabled soon after the second activate command. However, since the deviation in bitline voltage does not exceed a reliable sensing threshold, the sense amplifier amplifies the value on the bitline randomly due to noise originating from random physical processes. And the bitline goes either towards VDD or towards minus VDD. And we exploit this behavior and develop a high-throughput TRNG that leverages the random values on the sense amplifiers generated by QUAC operations. We will look at an example on how QUAC-TRNG exploits the high bit level parallelism and the massive parallelism in DRAM arrays to generate random numbers at high throughput. Here's a set of 4 consecutive DRAM rows which we refer to as a DRAM segment. QUAC-TRNG generates random values on the sense amplifiers in 4 steps. First, it initializes the DRAM segment using a predefined data pattern. In this example, we will fill the odd address rows with all zeros and even address rows with all ones. Second, it performs a QUAC operation to generate random values on DRAM sense amplifiers. At step 3, QUAC-TRNG reads the random values on the sense amplifiers to the memory controller. To do so, based on a one-time characterization effort, which I will describe in the next slides, it partitions the data on the sense amplifier into arbitrarily sized blocks. Each of these blocks have 256 bits of collective Shannon entropy. It reads each of these blocks to the memory controller and uses the SHA-256 cryptographic hash function to post-process each block and to finally produce a 256-bit true random number. QUAC-TRNG generates a 256-bit true random number for every one of these blocks it reads from a segment. So I will move on to our evaluation of QUAC-TRNG's randomness characteristics, its quality, and its throughput. I will also describe sensitivity studies we conducted to understand how randomness in QUAC operations change with temperature and change over time. We conducted a characterization study on 136 real DDR4 chips from SK Hynix to both understand the randomness characteristics of the results of QUAC operations and to evaluate QUAC-TRNG. We use a modified version of SoftMC, which is a DDR4 memory testing platform that lets us issue arbitrary DDR4 command sequences with any set of timing parameters to DRAM modules. We use rubber heaters and a temperature controller to maintain the temperature of the DRAM chips during our experiments. We use Shannon entropy to measure randomness in bit streams generated on DRAM sense amplifiers. Shannon entropy is calculated using this formula, and it can be interpreted as the effective number of random bits in a bit stream. To calculate the probability values in this formula, we simply find the proportion of logic 1 and logic 0 values in the random bit streams we test. To calculate the Shannon entropy for each bit line, we repeatedly perform QUAC operations and read the sense amplifiers 1,000 times. The intuition here is that a bit stream full of repeating values, such as all ones, will result in 0 Shannon entropy. However, a bit stream with an equal amount of zeros and ones will result in 1 Shannon entropy. We conduct a characterization study at 50 degrees Celsius and at nominal DDR4 voltage. In this study, we collect 1,000 bit streams, 1,000 bit streams from each bit line in 8,000 DRAM segments using all 16 different 4-bit data patterns. Each bit in the data pattern corresponds to the binary value we use to initialize all cells in a DRAM row. And for example, the 4 ones data pattern initializes each row with all ones, and the 1000 data pattern initializes the first row with all ones and the remaining rows with all zeros. We look at the cache block entropy to understand the effect of data patterns on the entropy resulting from QUAC operations. We calculate the entropy of each cache block as the sum of the entropy of all bit lines in that cache block in every segment we test. Based on this cache block entropy, we define 2 additional metrics. The average cache block entropy is the average entropy of each cache block in a DRAM module, whereas the maximum cache block entropy is the greatest cache block entropy in a DRAM module. So on this plot, we display the cache block entropy on the y-axis over the data patterns on the x-axis. The blue bars show the average cache block entropy, and the red bars show the maximum cache block entropy. These values are averaged across all DRAM modules we test. The bars are clustered according to the data pattern we use to initialize the DRAM segments. The error bars on the columns show the range of the values across all modules, where the upper tick indicates the maximum and the bottom tick indicates the minimum value. So notice that the maximum possible value for cache block entropy is 512 because there are 512 bitlines in a DRAM cache block. We observe that the entropy varies with the data parent. We exclude the 8 other data parents that cannot induce significant entropy on DRAM sense amplifiers from this figure. We observe that the 0111 data parent results in the highest average entropy across all modules. Since the first row is activated slightly earlier than the other 3 rows, we hypothesize that when the simultaneously activated 3 rows are initialized with the inverse of the first row's data, the bitline voltage cannot exceed the reliable sensing thresholds in most sense amplifiers, resulting in random values on a larger majority of the sense amplifiers. To see if entropy changes according to the physical location of the DRAM segment, we look at each segment's entropy. We calculate the segment entropy as the sum of entropy of each bit line in that segment. And the maximum possible segment entropy is 64,000, as there are 64,000 bit lines in a DRAM segment. We plot the segment entropy on the y-axis or the segment ID on the x-axis. And now there are 3 curves on this figure. The red curve shows the average segment entropy across all 17 modules. The error bars show the range of the segment entropy across all modules. And the dashed blue curve and the dotted black curve display the segment entropy for 2 selected modules, each representing a main entropy variation trend we observe across all modules. We observe that the segment entropy behavior changes from module to module, and the entropy of the segment in the middle of this highlighted region behaves in an inverted way for the 2 selected modules with different entropy trends. We also see that the entropy significantly increases near the end of the DRAM bank, around the 8,000 segment. We look at the distribution of entropy across all bit lines in an average DRAM segment in cache block size blocks. Here we see that the average entropy increases towards the middle of a DRAM segment. And to summarize, here are the key takeaways from our analysis of entropy. We see that the segment entropy changes according to both the data patterns used in initializing DRAM segments and the physical location of DRAM segments. And we attribute these to both systematic manufacturing process variation and design-induced variation-related effects. And to understand QUAC-TRNG's random number generation quality, we conduct 2 experiments. First, we collect 1 megabit bit streams from each bit line in every segment from multiple modules using QUAC. And we do this to show that QUAC operations can generate true random values on sense amplifiers. For the second experiment, we collect 1 gigabit QUAC-TRNG bit streams using high entropy DRAM segments from multiple DRAM modules to assess the quality of QUAC-TRNG. We input these collected bit streams to the NIST statistical test suite in our evaluation. In the first experiment, we collect large bit streams from multiple DRAM modules. Then we post-process them using the von Neumann corrector and input the resulting 1 megabit bit stream into NIST STS. This way we can test the stream generated by continuously sampling a single sense amplifier after QUAC operations is in fact generated by a true random number generator. In the second experiment, we simply collect large 1 gigabit bit streams using QUAC-TRNG and evaluate them using the NIST STS. We show in the paper with what significance each statistical test in the suite passes when input with our bit streams. And you can see the results for each experiment under the 2 columns. What these results show that is both QUAC and QUAC-TRNG generated bit streams pass all NIST tests and are therefore we can regard them as high quality true random number generators. Now we estimate QUAC-TRNG's throughput for a DRAM module according to this formula. Here, SIB is the number of SHA input blocks in the highest entropy DRAM segment, and L is the latency of executing 1 QUAC-TRNG iteration in nanoseconds. We refer to a contiguous range of cache blocks with 256 bits of collective Shannon entropy in a DRAM segment as a SHA input block. In this example, there are 4 arbitrarily sized SHA input blocks, and we identify these by rigorously characterizing DRAM modules for entropy resulting in QUAC operations. As an example, this figure plots the entropy of individual cache blocks in a high entropy DRAM segment. And to identify a SHA input block, we find a set of contiguous cache blocks that have a total amount of 256 bits of entropy. We calculate L by tightly scheduling the DDR4 commands required to perform QUAC operations. And we multiply by 256 as each QUAC-TRNG iteration outputs a 256-bit true random number. For our throughput estimation, we evaluate 3 configurations for QUAC-TRNG. The first configuration, which we name one bank, uses a single DRAM bank. The second configuration, BGP, exploits the bank group level parallelism in DDR4 to parallelize the DRAM commands required to perform QUAC operations across different DRAM bank groups. QUAC-TRNG's third configuration, RC plus BGP, uses row clone to bulk initialize DRAM segments row by row in DRAM, and it also exploits bank group level parallelism in DDR4. We use the priorly proposed row clone operations to bulk copy data within a DRAM subarray to reduce the overhead of initialization. And to do so, we use activate, pre-charge activate commands with reduced timing parameters and perform row clone in real DRAM chips. Here we plot the average, maximum, and minimum throughput calculated for each configuration across all DRAM modules. On average, QUAC-TRNG provides 3.44 gigabits per second true random number generation throughput, and its throughput is greatly improved by row clone, as it significantly reduces the overhead of initializing DRAM rows. We conduct a system performance study using Remulator to understand how fast QUAC-TRNG can produce random numbers, assuming an ideal memory scheduler that can generate random numbers using QUAC while the DRAM bus is idle. And this plot shows the throughput QUAC-TRNG can provide in a 4-channel system without negatively affecting the total off-chip memory bandwidth. And we see that QUAC-TRNG can achieve 74% of its empirical average throughput in such a system. Finally, we compare QUAC-TRNG's throughput against 2 of the high-throughput state-of-the-art DRAM-based TRNGs. We calculate both DRange's and Tolukter's mechanism's throughput by tightly scheduling the DDR4 commands required to induce timing failures. And we augment both mechanisms by exploiting bank group level parallelism and by using row clone to bulk initialize DRAM rows where we can. In our evaluation, we consider a base version for each mechanism where we evaluate them as they're proposed, and an enhanced and more fair version where we characterize the entropy resulting from timing failures using 17 DRAM modules and use SHA-256 to optimize their throughput. And we assume a system which has 4-channel DDR4 memory. And this plot shows the average throughput of timing failure-based mechanisms along with QUAC-TRNG in a 4-channel system. We project the throughput of prior work in QUAC-TRNG to various DDR4 data transfer rates displayed on the x-axis. And we conclude that QUAC-TRNG outperforms the base version of the best prior DRAM-based TRNG by 15 times at a standard 2.4 gigatransfers per second DDR4 transfer rate. And it outperforms the optimized version of the best prior DRAM-based TRNG by 2 times at potentially a future 12 gigatransfer per second data transfer rate. So we can see here that QUAC-TRNG and Tolukter's mechanism is not bound by the DRAM access latency, whereas the DRange is bound by the DRAM access latency in throughput. We compare against other slower DRAM TRNGs as well. You can refer to our paper for more details. We calculate the memory overhead of QUAC-TRNG and find that it occupies only 192 kilobytes in a DRAM module. Here you can see a breakdown of this memory overhead. We use 4 segments to perform quadruple activation, and we also reserve 8 DRAM rows to use the source operands for bulk initialization. Now, the total memory overhead amounts to 0.002% of the capacity of an 8 GB DDR4 DIMM module. As for the area overhead, we need to store 326 bits in a memory controller to enable QUAC-TRNG, and these are required to point to the segments that generate the random numbers. Again, to point to operands used as source operands for row copy operations, and to 256-bit entropy blocks within the DRAM segment. We model this overhead using cacti and find that it's negligible. Together with the SHA-256 accelerator, the additional area amounts to 0.04% of the CPU developed with a 7 nanometer technology node. Finally, we conduct 2 sensitivity studies to investigate the effects of temperature and time. In this study, we use 5 DRAM modules and initialize DRAM segments with the highest average entropy data pattern, which is 0111. This figure depicts the average segment entropy in 2 groups of DRAM chips with increasing temperature. We split the DRAM chips into 2 groups based on the entropy variation trend they show when temperature increases. And we observe that entropy changes with temperature, either decreasing or increasing as temperature increases. We check the average segment entropy in our chips at the beginning and at the end of a 30-day period, and see that it only changes by 2.4% on average. And we conclude that the characterized QUAC entropy is valid for at least 30 days. Now, I would like to wrap up with a summary of our work. DRAM-based true random number generators can provide high throughput and low cost true random number generation to a wide range of systems. And the problem with prior DRAM-based TRNGs is that they're slow. Our goal in this work is to develop a high throughput and low latency TRNG that uses commodity DRAM devices. We observed that a sequence of DRAM commands can activate 4 DRAM rows in quick succession, which we refer to as QUadruple ACtivation. Our key idea in developing a high throughput DRAM-based TRNG is to use QUadruple ACtivation to generate random values on DRAM sense amplifiers. We evaluate QUAC-TRNG using real DDR4 chips and find that it achieves up to 5.4 gigabits per second throughput per DRAM channel and provides random numbers with low latency. We compare QUAC-TRNG against the state-of-the-art DRAM-based TRNGs and show that it outperforms prior DRAM-based TRNGs. And finally, we evaluate QUAC-TRNG's quality using standard NIST randomness tests to show that it's a high-quality true random number generator. With that, I think I'm done. And thank you for listening, and I can take questions now.
Thanks, Ataberk, for that wonderfully detailed talk. So we have a couple of interesting questions off of YouTube, actually, and so I'd like to go through those first.
Sure.
So the first question is, it's asking that, is it possible that a malicious party might somehow hijack the process of QUAC-TRNG somewhere, say, in the middle of the algorithm, and potentially affect the randomness of the results? So, you know, maybe make the pattern more predictable, or really anything. Have you thought about that at all?
Yeah, I haven't thought about that, but I think there are ways to do that for like any type of true random number generator. One way would be to, based on our analysis, I can say, depending on the chip, for example, you could either increase the temperature a lot or lower the temperature a lot. And then by doing so, you would make sure that no or very small amounts of entropy is generated by QUAC operations. And then afterwards, what you get would be less random output from that TRNG. So I can imagine that being a possibility. And there could be other ways of doing that also. Yes.
Yeah, as a follow-up to your example, actually, in the case that say the adversary did manipulate the temperature and affect the amount of entropy generated, would that simply be a throughput loss, or would it actually compromise the randomness of the output?
So assuming that this system we build around QUAC-TRNG is aware of such an attack, it can certainly like take precautions. You could, as we did, you could characterize the entropy at various temperature levels. Like you could go to extreme temperatures, and then you would still be able to collect enough entropy, 256 bits of entropy in a SHA input block. And that would mean that you would lose a lot of throughput, but your TRNG remains safe or secure. So I think the answer is yes. Yeah, it will result in throughput loss in this case.
Okay, no, that sounds good. Thanks for explaining. So another question that we have here is, again, related to the source of the randomness, right? So certain pseudo-random number generators can also potentially pass these randomness tests. So the example provided was this Mersenne twister algorithm that's pretty widely used. And so if you know the internal state of this algorithm, you can predict the output that will happen, right? So from this, we can conclude that these statistical tests can, verify the quality of the random number stream, but they can't necessarily verify that the underlying physical process is truly random, or if there is a physical process at all, let's say. So is it somehow possible that in the case of QUAC, say, if we could potentially measure the the sense amplifier inputs with very high resolution through some mechanism, would that actually allow us to predict the following outputs potentially?
I think the answer to this is if you can measure it without inducing any type of state change, like within the sense amplifier, then probably yes. Like when you perform a QUAC operation, at that point, if you could probe the bitlines or the sense amplifiers, you could potentially foresee where the, I guess even then the answer will be no, because the hypothesis we have is real. I'll try to explain it again. So we keep the bitline voltage under reliable sensing thresholds, and then the sense amplifier, due to some random physical processes, randomly amplify this voltage to either VDD or 0, and then we obtain the random number. So even if you were to observe the bitline voltage being under the reliable sensing threshold, then it doesn't guarantee that your prediction would be correct. Like, so what I'm thinking of is that you would basically sample this sense amplifier. You will model the sense amplifier by observing what happens in many cases when the bitline voltage is below the reliable sensing thresholds, and from that you shouldn't be able to make a guess. And I guess that's why it will be a true random number generator. But maybe there are other ways of measuring the physical process that's going on in there that I don't know of, that I cannot think of right now. Then potentially, yes, maybe.
Oh, yeah, thanks. I think your response makes sense. And regardless of whether such a hypothetical scenario is possible, the QUAC-TRNG algorithm clearly still has value and exhibits the behavior that we wanted to exhibit. So it's an interesting thought experiment. Okay, thanks. So I think that covers the YouTube question. So I'll sort of stop speaking. If anyone else within the Zoom meeting wants to speak up and ask a question, now's a great time.
Maybe I'll say something. Can you hear me?
Yes.
Related to the previous comment, maybe not not so much of a question, but thanks, Atabek, first of all, for the nice presentation. Certainly, this is very interesting work. I think the thought experiment that was asked on YouTube is really a good one. It's always good to question whether something is truly random or not. And I think in the end, it's very difficult to prove whether something is truly random, right? Because we do not know whether there will exist a device that can do the measurements that we discussed. And even if it does, then it may be prohibitive to use that device on DRAM. And I think it is actually. So it's certainly what Minesh said earlier is true. The work is still valuable, but it's always good to ask the question whether it's really truly random. And that's the difficulty with truly random, true random number generators in general, right? Mm-hmm. So maybe 20 years or 30 years down the road, there will exist such a device that can show that can see the patterns here, right? I don't know. Okay, yeah, but today it's difficult. I had one other question, I think. That's maybe other people have questions also, but I will ask mine, and then they can continue. So you have, I think, QUAC-TRNG is certainly nice for some of the use cases that you discussed, like processing in memory, for example, right? If you have a processor or computation mechanism on the memory side, you don't want to go to some other chip or accelerator to generate random numbers if you need random numbers over there. So certainly, processing in memory is a very good use case for doing random number generation inside main memory. I don't think it's disputable. But the question I have is, how good is this random number generator, or how useful is this if you actually want to use it in a compute-centric CPU or GPU, for example? You want a random number in your CPU, GPU, or some accelerator. Then what benefit do you get compared to random number generators you can add to those chips?
That's a good question. I think the first trade-off there would be silicon area. Assuming you have a processor that cannot do true random number generation, doesn't have a way to sample randomness, physical random processes, and is still equipped with a DRAM device, then you can use this DRAM device to generate true random numbers. And I guess this is an analysis we haven't done, but the DRAM device fundamentally provides a very high, very high throughput to random numbers, because we can exploit the massive parallelism of DRAM arrays. So in the specialized device that you would implement within the processor, I guess, how many of them would you need to put there to match the bandwidth that a DRAM array can provide you? As I guess it's not clear how that would compare, but that's another thing that I can think of. Yeah, I think those are the 2 points that I'd like to make. Yes.
Yeah. So basically, your argument is, yeah, you don't need much changes to enable this, and the second argument is you have a lot of parallelism in DRAM.
Yes.
Yeah, I think I agree. Although I think on a device like CPU, for example, you can clock things with high frequency, very high frequencies, and you can probably get a very high throughput random number generator. But of course, that comes at additional energy cost. Yeah, I think that analysis requires perhaps some future research.
Yes, I would say so.
Okay, cool. Yeah, I don't have any other questions at the moment, so maybe Minesh or others can go ahead.
Certainly. So I have a question of my own, actually. So I'm wondering whether you've thought about whether sort of these types of principles that you use for QUAC can apply to potentially some other memory technologies, right? So for example, if we have SRAM arrays, could we similarly issue a sequence of operations that invoke this non-deterministic behavior? I'm just wondering what your thoughts are about that.
Yeah, as far as I know, SRAM devices or SRAM arrays are designed in a similar way to DRAM arrays. So you would have a sense amplifier, a bitline bar, and the word lines. So assuming that is the case, it should be possible to initialize multiple DRAM cells on the same bitline with conflicting data and activate them at the same time to keep the bitline voltage below the reliable sensing threshold. And then you can generate two random numbers in SRAM with quadruple or multiple activation as well. It's just that I think there are no commodity SRAMs that would allow you to do so at this point.
So I have a follow-up question. So follow-up to both Onur's and Minesh's, actually. So if we consider these UpMEMS processing memory chips, for example, what are the trade-offs that you see over there, like in a specialized hardware into that DRAM chip to generate random number, or using the DRAM array? Or is it a use case that makes sense or that doesn't make sense? I don't know. So what do you think about that particular use case?
So you're suggesting that, or asking if it makes sense to have in DRAM to random number generation in a device like UPMEM, right?
Yeah, so does it make sense for them to implement this necessary circuitry for QUAC to work?
Yes, so within DRAM, you won't need any additional circuitry. And I guess what you're asking is if it's worth it for them to implement a post-processing function within the UPMEM, the rest of the UPMEM chip. So I'll say, without being 100% sure, that you could potentially do post-processing using what UPMEM, for example, already has implemented there computationally. Like you could design an algorithm, and then you can still use QUAC-TRNG or other DRAM TRNGs to generate two random values within the DRAM chip without extra cost, and you would fetch the random bitline values to the computation chip and do some post-processing over there, if in case you didn't want to implement a lightweight post-processing function or an accelerator in the compute side of the chip.
Yeah, that makes sense. Thanks.
To quickly follow up about the post-processing, I'm curious what motivated you specifically to choose the SHA algorithm that you use in this work, and would potentially other post-processing methods work equivalently, or what trade-offs would be involved?
So I think two things. First one was that when we were looking at the prior work and what hash functions they use, we saw majority of them use the SHA family, and specifically SHA-256. And then the second point was because SHA-2 or SHA-256 it can be implemented in silicon with low cost. You can design an accelerator, like basically develop an accelerator, and it will take small area. It can operate at high frequencies, basically provide high throughput at low area cost and energy. And that's why we went for the SHA-256. But basically any cryptographic hash function that provides similar functionality to the SHA, basically mapping from a large input space to a smaller output space as uniquely as possible, should work. However, they could have different characteristics in terms of the hardware implementation. And then you could go back to choosing SHA in the end, or maybe another lightweight hash function.
Okay, yeah, that makes sense. Thanks. Okay, do we have any more questions for Ataberg? We're also monitoring the YouTube chat, so if there are, please go ahead and ask.
Maybe I'll ask one related to the results. Can you hear me?
Yes.
Okay. Okay. So you reported results from a lot of modules, but they all belong to only one manufacturer, SK Hynix, right?
Mm-hmm.
What is the reason? Okay, maybe I should say, can you explain why you got only one manufacturer? Because I think I know the backstory of some of this. And the second question is, how fundamental is this phenomenon across all DRAM? I think you kind of answered that, but I think it's good to emphasize a bit. Yeah, how fundamental it is it?
Okay, yeah, maybe I'll start by the second question, by answering the second one first. So since this is closely related to how sense amplifiers operate, and we have them in every DRAM chip, this phenomenon should be, everyone should be able to observe this in any DRAM chip, assuming that you can isolate the DRAM array. However, the reason why we cannot, why we didn't evaluate other modules from other vendors is because we couldn't observe QUAC in other vendors, meaning that we couldn't activate 4 DRAM rows at the same time, not meaning that we weren't able to observe random values. It's just that for some reason, with the same DRAM command sequence, the other DRAM modules from other vendors do not end up activating 4 DRAM rows. So I think there is something different in the row decoder circuitry, or there is some type of filtering mechanism that would dismiss the commands that violate timings, and that ends up not being able to open the 4 rows, basically.
Okay. Yeah, I think maybe we can delve a little bit deeper into this because there are multiple reasons why that may not work. One is, as you said, perhaps some manufacturers don't allow you to violate the timings, right? Mm-hmm. Then, of course, you cannot even test any hypothesis that mm-hmm. violates the timings. So that's why it's not doable. But if you could somehow violate the timings, perhaps you would see similar behavior, right? But we cannot verify that, of course. Mm-hmm. Yeah, I think maybe this goes back to the nature of the work, right? You're trying to do this on commodity DRAM chips. You're trying to do basically perform an unsupported operation on commodity DRAM chips and show the value of that unsupported operation.
Exactly.
Even though the DRAM chip was not designed to support that operation, clearly, right? Mm-hmm. In a sense, maybe we're kind of lucky to see that we could observe this on a large number of chips from one manufacturer. But if this becomes a supported operation, of course, clearly it becomes, it can be designed to be much more reliable and robust, and it could be actually performed by any DRAM chip, right? Maybe you could comment on that, what it takes to make it a supported operation.
So thinking of it from the standards perspective, like the DDR4 standard or any new DRAM standard, since we can do this operation in at least one vendor without any change to the standard, so the standard commands itself, the required changes in the interface, I think, is negligible. You wouldn't need to add any, I guess, at least additional pins. Perhaps you would need to add a new command for quadruple activation, but thinking of it a bit more in detail, I don't think you need that. And to give an example, there is this new Samsung HBM PIM device that can perform PIM operations in one mode and regular accesses in another mode. You could have a similar functionality. You could implement a similar functionality to support QUAC-TRNG or QUAC operations. So to summarize, you wouldn't need to modify the interface. And within the DRAM arrays, I think, or within the DRAM chip, I don't think the row decoder design fundamentally disallows this type of an operation. Clearly, one vendor allows this. So at least what I think is, if someone wanted to support this and it's not supporting it right now, like the other vendors, they could at least partition some of the cells or some of the rows or a subarray and implement a similar row decoder circuitry that we described in the paper. Then they would have enabled QUAC in their modules. So to summarize, I think the standard doesn't need to change in the best case or in the worst case. And the DRAM chip should be minimally modified to support QUAC in the worst case.
Okay, yeah, that makes sense. I think I agree with you that given that this is already doable on commodity DRAM chips, it doesn't require much support to actually become a supported operation, right?
Yeah, exactly.
It may need some, of course, wording in a document, like a data sheet, to say that this is what you would expect if you do quadruple row activation using maybe some command sequence, right? Yeah. Okay, cool. I don't have any other questions. Maybe there are some questions on YouTube, but I'll leave that to Minesh and Kirai.
Yeah, so it's perfect because we do in fact have a question on YouTube. So it sort of follows up from the discussion we just had, and so this is maybe more in the context of, not so for example, the modules that you tested and verified this behavior on, if I used one of those in my personal computer, say, what might it take to actually get it to generate random numbers for my C application? For example, if I'm writing a simulator, what would I need to do? What would that look like?
By plugging in one of the devices we tested to a commodity system, I think you wouldn't be able to generate random values the way we do, because as far as I'm aware, like current computing systems, the chipsets or the processors, they don't let you access DRAM with arbitrary timing parameters. So if you could, if you don't need to use DRAM as main memory, you could have a test bed, I think, if your motherboard supports changing the timing parameters. And then what you would do is to issue a sequence of read and write commands or read and write load and store instructions to first initialize the segment and then activate 2 rows by using those load and stores, solely loads and store instructions to perform a quadruple activation operation. So I think it's, unless I'm missing something, it shouldn't be possible to use QUAC, to integrate QUAC tightly into a real system right now with the contemporary motherboards and chipsets we have.
This makes sense, and I imagine the paper talks a little more about the requirements from memory controllers and so forth to enable this.
Mm-hmm.
Okay, thanks, Atabak. Okay, I don't think we have any more questions for the time being. Owner, would you I don't know if you have any more questions or you'd like to do next?
Thanks, Minesh. Maybe I don't have questions, but maybe I have a comment related to the last question. I mean, if your memory controller is somewhat programmable to support operations like this, potentially you could do it in a real system, right? But existing memory controllers are not as programmable as we would like currently. So that's one of the reasons why it cannot be done today, right? But all you need is a memory controller that can perform these operations that you want, QUAC operations. And that's enough. I guess you do need to perform the post-processing as well, right?
Exactly.
So you do need that in the memory controller as well. So that also requires some effort to implement. But yes, I think if you have some programmability and logic in your memory controller, if we had configurable and reconfigurable and programmable memory controllers, we could have done it in existing systems relatively easily, right? Okay, I don't have any questions. It seems like there are no other questions. Thanks, Atabak. This was a nice talk. Okay, maybe I have one more question before we leave.
No problem.
Because this is, I think, something we may want to think about going into the future, or other people also may want to think about. Is this the best you can do in random number generation in DRAM?
I would say, sorry, were you done? Sorry for interrupting.
Yeah, there certainly has been a flurry of works in DRAM random number generators, right? 2 of which you compare to extensively. Actually, you compare to many of them in the paper, but 2 of which you highlighted a lot in this talk, since they're the highest performance ones, best previous ones, let's say. And this is yet another DRAM true random number generator. But will there be one that's better than this going into the future?
Probably yes. Just by judging by the amount of entropy we generate in a DRAM row, is still we still have a high, very large headroom there. So we have 64,000, for example, bit lines in a DRAM row, but even with QUAC-TRNG, which is the highest throughput TRNGs in DRAM for now, we can only generate around 2.5 thousand bits of entropy, meaning that we have that huge 61 to 62,000 bits that we can still potentially generate random bits that we can generate from one row activation. And I currently am not aware of any new mechanism that can do that. But there could be others that could essentially generate more entropy than what QUAC does, and then that would result in a higher throughput TRNG.
Mm-hmm. Yeah, certainly that's the subject of future work also.
Mm-hmm.
But currently, this is the state of the art, right? In,
yes.
in DRAM based to random number generation.
Mm-hmm.
Okay, cool, excellent. Thanks for the talk and thanks for the questions. And we look forward to your future works.
Thanks, and I hope this was fun and let's say enlightening for the audience and everyone that viewed the YouTube live session. I think live session. Yes, thanks, Onur and Minesh and Giray for the questions.
Yeah, thanks. I hope so too. Thanks.
Okay, goodbye.
Okay. Bye, everyone.